So now I have to talk about some physics. Carnot cycle. Going back to our Carnot cycle, that's what it did, right? What do you think a reverse Carnot cycle would look like? Excellent. Like that. 1 to 2 to 3 to 4. And this is the hierarchy of what is happening. Note, for all future engines, whether it be for your cars, except for the jet propeller people, right? Jet engines, except for those, every other cycle that we will do from power plants to cars to diesel to all other kinds of engines will always have 4 components that are these: compressor, condenser, turbines, and evaporator. Whether they work this way or whether they work this way. Okay, so a reverse Carnot cycle. What do we know about a Carnot cycle? Feel free to look it up. That a Carnot cycle is made up of 4 processes, well, 2 basic processes. What were they? Good. So a reverse Carnot cycle must also be based on 2 processes which are reversible, which will be isothermal and adiabatic. What is an isothermal process? Good. What's an adiabatic process? Can I call the adiabatic process? Okay, do we remember our second law of thermodynamics? What was it? Well, that's also true, but in terms of Q and T's. Wasn't it something like this? So if Q is 0, can I call delta S as 0 as well? Reversible ideal process, and you're right, delta S will be equal to 0. So may I also call this process isentropic? The reason why I'm introducing isentropic is because if you ever read another textbook, say for example, where you will actually go in and do all your studies for your refrigerators, they will call it an isentropic process. All that means is delta S equals 0 for these processes. That's literally all that means, which is a byproduct of the second law, which was here.
Is it isentropic or isotropic?
Isen. Because it's entropy, so it's isentropic. There is an N in it. Okay, so which ones of these are isothermal and which ones of these processes are adiabatic? Does it look something like this? Okay. So this will be at TH. This will be at TC. And this is adiabatic. And this is also adiabatic. Do you guys agree with that? So steps 2 to 3. Is that a compression step or an expansion step? Excellent. Step 2 to step 3. It is a compression step Work is being done on so what do we call this system now? What will we call it? Remember it was work done on the gas. In this case, it will be called the working fluid. This is an isotropic step. That means delta T will be 0 and TH will be maintained. Step 3 to 4. That's an adiabatic step. That means QH will be 0. Step 4 to 1. Will be an isothermal expansion, right? Work is done by the working fluid. And steps 1 to 2 will be adiabatic step. Again, where TC goes to TH, right? Very, very quickly. So as always, we want to find how efficient our system is. So what did we call our efficiency? COP. For a reversed Carnot cycle will be given by QC over W in, or QC divided by QH minus QL with a minus sign. Actually, I should call it C. May I now write from the second law delta S equals Q over T? So can I write Q as T delta S? So if I plug this in here and in here, will I get T delta S divided by T delta S minus T delta S? Now, this should be, guys, can I have you pay attention? This would be C, this would be H, and this would be C. Which are the steps in which these will occur? 4 to 3, 2 to 1, and 4 to 3. For an ideal, absolutely perfect situation, can I call delta S's the same? Only for ideal, perfect transformations may I call delta S 4, 3 the same as delta S 2, 1? So I am left with COP of the Carnot cycle as TC divided by TH minus TC. Oh, why do I have a, or 1 over TH over TC minus 1. COPR for a Carnot cycle. we can do the exact same steps and figure out that COP for the heater actually comes out to be 1 over 1 minus TC over TH. Have we seen 1 minus TC over TH before? For the Carnot cycle? We actually write
The weird symbol. I don't know the name of it. The efficiency.
the efficiency. Do you remember doing that?
Yes.
And I made you put it into a green box. So what's the relationship between COP and efficiency? It's 1 over.